she will speak about one of the results we obtained, and this is also something she will put into her PhD thesis. So, I suppose that she will, or I hope, she will soon write.
Thank you for the introduction. Good morning, everyone. The problem that I will present today may seem to be very simple or even trivial, but it turns out to be very mathematically interesting and quite important for quantum information theory. And as it was announced, this is one of the parts of my PhD research and joint work with my supervisor. Before I will present the problem, I will tell you something about the motivation of our work. So our research concerns the universality and optimality in quantum computing. However, before we go to quantum systems, let us start from the notions from classical computation, because from mathematical point of view, quantum computing is the extension of classical computation. So classical computers are the systems using Boolean logic, and the operations are performed on so-called bits, and every bit is an object that can be in one of two states, 0 or 1, and operations performed on bits are Boolean functions. Every such a function can be expressed as a sequence of elementary blocks called logic gates. And the most famous examples of logic gates are AND, OR, XOR, NAND gate acting on 2 bits, or NOT, which is an example of a 1-bit gate. And from these logic gates, one can build an arbitrary Boolean operation. For example, let us consider the operation which is called 1-bit full adder, which adds 2 bits, taking into account the so-called carry in bit, which comes from adding bits on the previous stage with smaller significance. So such a adder consists of 2 XOR gates, 2 AND gates, and 1 OR gate. And it has 3 inputs, A, B, and C in, and returns 2 outputs. The first one is the sum, and the second one is the carry in bit. In general, a Boolean function operates on k inputs and returns n outputs, and there are arbitrary integers. And an example, for example, of more complicated operators, let us consider a function which adds 2 4-bit numbers denoted by A and by B. And as one can see, this function consists of 4 blocks, and each of these blocks is exactly this 1-bit full adder. One can easily count that this function has 4 inputs. There are 4 bits of A and 4 bits of B, and also as an input it has carry in bits. It returns the sums corresponding to each of 4 bits and the carry in bits. Having defined the gates, the gates and other important notions for classical computation, we can go to the level of quantum computation. So the different quantum computers and quantum differ significantly from classical computers because the operations are performed not on logic bits but on qubits, which are quantum analogs of bits. And a qubit is a two-level quantum object which can be in a state 1, 0, or in any superposition of these states. A D-level generalization of a qubit is called qubit. So in the simplest model, we can assume that our quantum system is that our quantum computer is an isolated quantum system which consists of n qubits, and the Hilbert space of such a system is the tensor product of one qubit Hilbert spaces.
Excuse me, I understand this right, that the rank of the level corresponds to the number of ground states possible for a qubit?
Yes, please.
Okay, I need to repeat. So do I get it right? If the rank of the level corresponds to the number of the ground state for a qubit, basically? Yes, so it's the number of the way that the wave function can collapse into.
Yes.
Okay, thanks.
And so every one qubit Hilbert space is isomorphic to a d-dimensional complex space. The operations, the basic operations performed on the qubits are called quantum gates, and because they are unitary operations, there are elements of the special unitary group acting on the space H. Among quantum gates, we can distinguish the gates acting on one qubit, and there are unitary operators belonging to this space, which is isomorphic to the group SUD, and the gates acting on more than one qubit, in general k-qubit gates, which are elements of this space. In our research, we concentrated on one qubit gates, and in the next slide, I will explain the reason.
I always had a problem understanding one thing. Going from classical to quantum, we pass from a discrete system to one that has infinitely many degrees of freedom. So in order to implement this, you cannot really deal with these general SU matrices, but with some discrete versions of this, because it must be implemented on the machine.
Yes,
this machine does not have infinite resolution.
Yes, of course, we take into account the fact that every operation can be performed only with some accuracy.
So this is later taken, because at this level, it seems that it is impossible to implement this because of this infinite number of degrees of freedom.
So let us assume that we have a set of finite gates denoted by U1 to UK, and that they are one qubit gates. If we every composite.
Much more of this quantum gates than classical, right?
Yes.
In classical computing, we can prove that the Turing machine can be built up with a very restricted set of gates. Is there anything like the Turing machine which what will be the subset of the quantum gates which is necessary to build it?
We also start from a restricted set of gates, compose them, and from these basic gates, we build with some desired accuracy And
Turing
it-
machine works with arbitrary accuracy.
yes, and also
Turing machine works with arbitrary accuracy, and there is a finite set of gates,
yes,
very trivial gates in some sense, which can theoretically perform any possible calculation with arbitrary accuracy.
yes, of
So
course.
the question,
Also in
well, we don't know whether it can stop, but that's the other issue. I mean, that's another issue. But the
Also-
question is, how is that in the case of because we don't need anything else. And
What do you have in mind by telling arbitrary accuracy?
sure, because the theorem says that if I have any arithmetic operation with arbitrary accuracy, richness of arbitrary accuracy, then I can build a Turing machine which can add them and divide them and do anything what I want with this number with the same accuracy as the number.
Okay.
So that's what the computer scientists are telling. I mean, it's because the Turing machine.
Sure, it shouldn't be mixed with infinite accuracy.
No. I didn't say infinite accuracy. I didn't say infinite accuracy.
Sure.
And the question is that in order to prove that the Turing machine does it, I only need the concept of bit and how the gate works on those bits, nothing more. Now we have the concept of these qubits and
Yes.
the quantum gates. And the question is, do we have something like, I know this is not the subject of the talk, but I mean,
Yes,
what will be, I mean,
yes, I
is
agree.
the quantum Turing, so let me restrict the question. Is the quantum Turing machine anything different from the classical?
Yes, and I would like to answer your.
Because the operation is to perform arithmetic operation. There are no different quantum arithmetic operation. Yeah, but that's mathematical mumbo jumbo. I have two numbers, and I can add these two numbers or multiply or whatever using a classical computer or a quantum computer. But these are the same numbers, and the outcome must be the same number. It's irrelevant who does it, right? So the question is whether this quantum computing machine which
Yes.
does this, can I replace the classical Turing machine which does this operation with something quantum?
Yes, sir, you can, and I would like to answer your questions on this slide.
So what is this? So what
There is an answer.
So this is exactly the answer of the answer.
What is H in the first line? H is C.
Yeah, H.
And the copies of C.
Yeah,
And the
this
copies
is.
of C.
In general, it is the Hilbert space of a system. But as I will show in a moment, we can restrict this. Well, it is in general a Hilbert space either of one qubit
On this
or
line it is CD. Yeah?
yes. Yes, this is the CD of the slide.
But I thought that this use can operate in different Hilbert spaces.
No, so H here, you can think about it as n qubit space or n unit space. So you have n particles. It doesn't matter what we put here now. So the same
Because
is definition.
The definition I will present is the general definition, and it is no difference. So let us define the set of compositions of the gates from the set S of the length n. In a quantum information community, such compositions are usually called words, and let us denote the set by Sn. So this is the product of UA1, UA2, up to UAN, where AI can be different or can be the same. And we say that the set generated by S, this is our notation, the set generated by our initial set S is the union of this set of words. This means this is the set of all the compositions of elements of S, all the words built from these gates of the length from 1 up.
This is a set of all possible product
Yes.
matrices.
Yes, exactly. In the limit.
Dimension.
Yeah, exactly. In the limit on infinite length. In order to have a group, because this set has not necessarily a group structure. So if you want to have a group generated by S, we need to close this set topologically, and the closure is denoted by overline. And now,
What does this mean in practice? I have these matrices, and I have the set of all possible products of these matrices. So how do I close them?
Taking all
Go
the
for it.
limits.
Yes.
All the limits. All
Yeah, taking all the limits, exactly.
operators which may be arbitrarily approximated by this.
In what sense the product is arbitrarily approximated by the product of matrices? In some, there must be some way of measuring this.
These are finite dimensional spaces, therefore topologies are equivalent. There is
Yes,
practically
exactly.
only one topology.
And then after this we can define the property of universality. So we say that our initial set S is universal if every unitary gate can be so again, we say that our initial set S is universal if every possible unitary gate from belonging to this group can be approximated by some element from the group generated by S with arbitrary accuracy. And this is exactly the answer to your question. Note that in this definition we assume that the Hilbert space is arbitrary. However, it was proven in 2002 that a universal set for n-qubit quantum computing can be constructed from the universal set of 1 qubit gates and an additional gate acting on at least 2 qubits, that is called entangling gate. So having 1 qubit gates and an entangling gate, we can build an arbitrary gate acting on this whole system. Among all quantum gates, especially important are qubit gates, because according to my knowledge, all existed quantum computers work on qubits. So qubit gates are elements of the groups of 2 by 2 special unitary matrices, and of course there's a lot of ways of parameterization of such gates. We assume the following parameterization, so where phi is the spectral angle of a gate, and k is the rotation on the blocks, is the rotation axis on the Bloch sphere, and x, y, z are the coordinates.
So notation is somewhat confusing because the thing in parentheses should be in front because it's not under the sign function.
Yes, it's not the argument of sign.
Yeah.
Yes.
So it's better to write it in front.
Yes, it's my fault. And important is that every qubit gate has a corresponding rotation matrix which describes rotation in 3 dimensions. Yes.
Is there an intuitive argument why do we need many of these Hilbert spaces? Because this one single qubit has infinite capacity. It has infinite be many possibilities. So why do you need more?
So basically, any number can be described by this single net.
So is there any reason that could be understood? Why do you need the set of all these Hilbert spaces?
Because you want to parallelize those
Yes.
stations.
Aha.
To do all options at once and not one
And
after
this
the other.
cannot be done on one
But,
qubit.
but since U is infinite in capacity in this
Yeah,
sense,
sure,
then I can write these numbers one after another, and that's well, what is one parallel in this case, right? I just write them one after another and use just one U. So, well, ale na jednej macierzy to zawsze się przeprowadza operacje jednocześnie.
Tak, ale jak chcesz mieć na dużym
No to
systemie...
na duży to nie ma sensu duży mały, bo to jest jedno U jest tak duże jak się chce. Well, the U is as big as you want.
U należy do S.
Note that,
But any real number,
excuse me,
arbitrary accuracy, and any number of real numbers with arbitrary accuracy can be written as a one U.
excuse me. We can discuss later. Note that the set S is universal only if the set generated by S is infinite, because otherwise we cannot approximate every unitary gate with arbitrary accuracy. In order to formulate a condition imposed on S such that the set generated by S is infinite, let us define the group elements of finite and infinite order. So we say that the unitary gate U has a finite order if there is some power n, which is integer, such that n raised to this power is equal to the group identity. Equivalently, we can write this like this. So this means that the spectral angle phi must be a rational multiple of pi, because otherwise U is an infinite, has infinite order. And there's a very important fact, which is known as Bernstein's lemma, and which is also true for matrix groups, that the set generated by S is infinite if it contains at least one element of infinite order. So if we would like to check if this will be infinite, we have to check if the elements of S or their products have infinite order.
Allowing for changing the coordinate system, because you have chosen certain direction, z direction, but
yes, but the
you could change the z direction and the definition will change because the meaning of phi will be different.
no, because phi is the spectral angle, so it doesn't change.
I understand this is the same phi as in your definition of U.
Yes.
So it depends on the orientation of the z-axis. If you change the orientation,
If I understand correctly, this is just the angle by which you simply rotate the, and k just picks the axis. So if you change the basis, you'll just change the components of k without changing phi.
but the element which is of finite order will not be of finite order. It will be.
It will be.
It will be.
Different orientation.
It's a differential angle, just not an arbitrary angle. It's a rotation angle, basically. Depends how much you rotate.
In the next,
In the definition of U is a spectral angle. If you diagonalize matrix U, it will have a spectrum.
It will have a spectrum e to I phi, e to minus I phi. So this phi does not change.
the spectral angle doesn't change.
Geometric has a geometric meaning. Yes.
Let consider a family of sets, which is very important for quantum information community. Each of these sets consists of a gate called the Hadamard gate, and the canonical form of Hadamard gate is given here, and the so-called T gate, which is a phase shift. Hadamard. This picture presents Hadamard gate and T gate on. It is known that this set for the angle phi equal to pi over 8 is a universal set of 1 qubit gates. However, note that in this case, both of these gates are elements of finite order, because the Hadamard gate is the rotation by angle pi over 2 around this axis. However, as it was proven by Chuang, the product of these gates is the matrix of infinite order, and therefore, by Bernstein lemma, we have that the set generated by these matrices is infinite. You would like? Yes, of course, they cannot commute nor anti-commute. So we would like to generalize this result and find angles phi for which the product of these matrices is infinite. In order to answer this question and simplify the calculations, let us write the rotation matrices corresponding to the Hadamard gate and the T gate, and let us define the rotation which is a product of these gates. The trace of this product is equal to minus cosine 2 phi. On the other hand, if we diagonalize this rotation matrix, then the trace of the diagonalized of this diagonalized O gamma k is of this form. So we have this equality. After some very simple transformation, we finish with this final equation when the angle gamma pi is gamma prime, is gamma plus pi. Because we want to change the sign of a cosine. Next, let us consider the family of gates, another family of gates which is also very important, and this is family of rotations around axis x, y, and z by angle pi divided by 2. And assume again that they are elements of finite order. This means the angle phi is a rational multiple of pi. We again want to find the condition for pi such that a product of arbitrary two of these rotations has infinite order, and hence obtain immediately the set generated by S, X, Y, Z phi is infinite. So let us again write down the rotation matrices corresponding to the gates, to these gates. Again, define the rotation which is a product of two arbitrary rotations. There's no difference between them. The only condition is that the the axis xy and xj must be, of course, different. And let us again write the trace equality. So after diagonalization, the trace is 2 cosine gamma plus 1. And on the other hand, the trace of this product has this form. And after transformations that are much more non-trivial than in the previous case, we obtain this equation. And note that this final equation is very similar to this final equation. So we have an algebraic equation with trigonometric functions, and we ask for which phi gamma is a rational multiple of pi. So from the first side, the answer seemed to be very difficult. However, using some facts and tricks from number theory, one can solve this problem quite easily. So in the next slides, I will present these facts and present some basics of algebraic number theory. So let us start from the most important definition. A complex number A is algebraic if A is a root of some polynomial with rational coefficients. And in general, a number of such polynomials can be infinite. The set of algebraic numbers is usually denoted by bold A. And the examples of algebraic numbers are, for instance, rational numbers, square roots, and, what is very important, trigonometric functions of angles that are rational multiples of pi. So this number is for sure an algebraic number, and this number also. And as I've just said, the number of the polynomials with rational coefficients for which A is a root can be infinite. However, among them, we can distinguish the minimal polynomial, which is the monic polynomial with rational coefficients of the possible smallest degree. And the relation between algebraic numbers and their minimal polynomials is unique, which is a very important fact. And to make the notion of the minimal polynomial more clear, I presented some examples. So the minimal polynomial of the number 2 is simply equal x minus 2. The minimal polynomial of the square root of 2 is of this form. These minimal polynomials are non-trivial and were computed in Sage.
The theorem that there is a single minimal polynomial, it is true. Is it difficult to prove, or
assume there are two unsubtractable. Assume there are two different unsubtractable. Because a lower degree polynomials.
So you can lower the degree and then you can put the coefficient next to the highest power.
Yeah, of course, the normalization is obvious, but otherwise it is a unique minimal polynomial. Czy to jest trudne do wchodzenia?
Trzeba rozważyć ideał wszystkich rozwiązaniów, które się stosują.
Tak.
Nie, w każdym razie nie jest wątpliwe.
To be honest, I've never seen the whole proof of this statement. There are some families of minimal polynomials that are characterized of very special and very nice properties. and which are, for instance, minimal polynomials of trigonometric functions. Let us start from the family of minimal polynomials of cosines of angles of this form. Because note that every angle phi, which is a rational multiple of pi, can be written as where p and q are integers. However, this expression can be rewritten as where k and n are coprime numbers. This means their greatest common divisor is equal to 1. And for each pi, which is a rational multiple of pi, we can find k and n such that this equality holds. So let us express the angle phi on this form. Then its minimal polynomial will be denoted by psi nx, which is the canonical notation. One can very easily check what is the form, what is the explicit expression of such minimal polynomial for small n. For example, for n equal to 1, the polynomial is of this form, and this is the polynomial of the first order. For n equal to 1, equal 2, we have that this is the cosine of pi. So the polynomial is of this form, and in general, we can write it. And then in general, it can be defined as a product over all cosines 2k over n multiplied by pi, where k is coprime to n, and k is smaller than n divided by 2. And another examples of these minimal polynomials that can be written by hand is the minimal polynomial for n equal 3 or for n equal to 4. For larger values of n, it is much more difficult to find the explicit form of this polynomial. However, there are formulae that make them dependent on Chebyshev polynomials. So for every n, we can find explicit form of psi n. A very important statement we have proven for this family of minimal polynomials is that such a polynomial is a polynomial with the non-integer free term if the angle phi is different from k pi divided by 2. So only if n is equal to 1, 2, and 4, we have that this minimal polynomial psi n is a polynomial with integer coefficients. If all other cases, this polynomial has at least one coefficient, which is a rational number, but it's a not integer. We do not know in general, or maybe we do not know in the general formula for the coefficients. However, we can very easily show that this non-integer coefficient is a free term. And the second family of minimal polynomials are the minimal polynomials of 2 cosine of k pi divided by n. A very important property of these polynomials is that comparing to these polynomials, they have only integer coefficients for all k and n. To znaczy, this means every...
Why 2 cosine and not just cosine?
Because
of the equation we want to solve. Because 2 cosine
Yeah.
equals 1 plus cos.
On the previous slides, there were
Yes,
statistical.
so we needed. We know that this is algebraic number, and this number is also algebraic. So we need to know the minimal polynomial of this number and the minimal polynomial of this number. So the minimal polynomial of 2 cosines has always integer coefficients for every n. And as for the roots of these polynomials, I will present them on this picture. So this is the plane of complex numbers in one dimension, real part and complex part, and the red dots represent.
That is now what was called psi, yeah? Minimal polynomial, yeah?
Yes, the minimal polynomials of double cosine will be denoted by eta, and the minimal polynomial of a cosine will be denoted by psi. So as long
too fast for me. Okay.
I'm very sorry.
Digest a little bit.
So important is that the roots of these polynomials are obviously different. And the roots of the polynomials of cosine, the roots of these polynomials for some n, I assumed on this picture that n is equal to 8, are denoted by gray dots, and the roots of the minimal polynomials eta n for n equal 8 are denoted by blue dots. So as one can see, the roots are different. So now let us return again to this equation. So we know the properties of this polynomial. We know the probable properties of this polynomial, but in fact we would like to know what is the form of the polynomial of this number. Because by the uniqueness of minimal polynomials, we know that if two algebraic numbers are equal, then also their minimal polynomials must be equal. So we would like to find the minimal polynomial of this number, of this sum. And it turns out that the problem of finding minimal polynomials of a sum or of a product of two or more algebraic numbers is a very non-trivial problem. However, it can be solved completely in some very particular cases. In order to do it, let us define the so-called companion matrix corresponding to the minimal polynomial MA. Companion matrix is the matrix having the characteristic polynomial equal to the polynomial MA. And the canonical form of such a companion matrix is written here. So if you compute its characteristic polynomial, it turned out to be exactly equal to this minimal polynomial. We know from linear algebra.
So every matrix capital M that corresponds to a minimal can be brought to this form.
Yes. Yes. However, of course, it's not a unique form.
Kolejne te wiersze, zostawiając ten, który
Next, let us define the matrices MAB and MA plus B. MAB is the Kronecker product of the matrices MA and MB, which are companion matrices for the roots A and B, and the same for the matrix A plus B. In this case, it is the so-called Kronecker sum of the matrices MA and MB. We know that if we compute the characteristic polynomials of this and this...
There is no requirement for the dimension of this matrix, because if you start with a relatively small MA, then you produce bigger and bigger matrices. No restriction for that.
In general, there is no restriction. And let us concentrate on this matrix. If we know that if we compute its characteristic polynomial, then it turns out that one of the roots of MAB, one of the coefficients of MAB is exactly this product, and in this case the same holds for this sum. So in some particular cases one can show, but it is very non-trivial, that if one of these roots is just a rational number, then the minimal polynomial of a product AB is exactly equal to the characteristic polynomial of this matrix, and the minimal polynomial of the sum A plus B is exactly equal to the characteristic polynomial of this matrix.
No matter, because this companion matrix, I understand, is it unique? This companion matrix M alpha, is it unique?
No,
Alpha?
No. This companion matrix is not unique.
Of course, this was my guess. Therefore, this result is true no matter which MA and M beta you take.
Yes.
Yeah? Ah.
Yes. However, it is not true in general. In general, this characteristic polynomial decomposes as a product of polynomials with rational coefficients, and one of these polynomials is the minimal polynomial of a product or of a sum.
When you know the minimal polynomial, is there a formula to calculate the coefficient C?
So coefficients C are coefficients of this minimal polynomial. So it's actually not really true that the companion matrix is not uniquely defined. When you have a minimal polynomial, there is only one companion matrix associated to this polynomial.
When it is of this
because it is this, yes, because but the coefficients of
for example, if you transpose this matrix, okay, you also... Yes. So in order to find the coefficients of the minimal polynomial of this number, we need to compute the companion matrix for the minimal polynomials of this and this number, and find the coefficients of this minimal polynomial. Because in this case, we have a sum of two roots, where one of them is a rational number. We have the equality, and the minimal polynomial of a sum is exactly equal to the characteristic polynomial of this matrix. So the characteristic polynomial. This is the companion matrix for the sum, for this sum, and minus lambda minus identity multiplied by x, and I have to compute the determinant of this matrix. And let us denote the coefficients of this determinant by omega I. If I use Laplace expansion along the first row of this matrix, I obtain this formula, and after some transformations, I finish with the following result. The coefficient omega d, which is the coefficient with the highest power of x, is of course equal to 1, which is good result because it is a minimal polynomial, and minimal polynomial is monic. The coefficients corresponding to power of x, which are lower by d, are of this form. So they depend on the coefficients ci, where ci's are the coefficients of the minimal polynomial of this number. And they depend also on some ai, aj, cj, where aj are some integers. So if we express the coefficients of this minimal polynomial this way, then we see that all omega i's are integers if and only if all the coefficients of the minimal polynomial of the cosine of phi are integers. So only if the minimal polynomial of this number is an integer minimal polynomial, then the minimal polynomial of this number is integer. But this is true only if phi is of this form. So only if I is equal to 0, pi, or pi divided by 2. In all other cases, at least one of these coefficients is a non-integer, but it is a rational number. But we know that the minimal polynomial of such a number must be integer. So if it is not integer, this means that the minimal polynomial of 2 cosine gamma is not the polynomial of this form. So this means that gamma is an irrational must be an irrational multiple of pi. And this is exactly what we did in our paper. So I again write down the trace equalities for the family 1 and the family 2. Compare the minimal polynomials, check for which angles phi the minimal polynomial or 2 cosine gamma has integer coefficients, and I obtain and I obtain the following result. In the first case, phi must be different. Gamma is a rational multiple of pi if and only if phi is of this form. This is the family with the Hadamard gate and the T gate. And gamma and phi is of this form for the family of rotation matrices. But what happens if gamma is one of these angles? So we have just proven that the product of the matrices is of finite order. And now I decided to write down these matrices explicitly and show that in this case the set S cannot be universal. So let us consider the family of Hadamard and T-phi gates. The Hadamard gate is always the same, but the T gate differs. And if phi is equal to 0 and pi, the rotation matrix corresponding to T is the identity. So this set is not universal. If the angle phi is equal to pi divided by 2, the matrices are of this form, and if we start to multiply them and consider products of arbitrary length and so on, we can see that we never obtain all possible rotation matrices. So this set is also universal. And the final case is the case when phi is pi over 4. We have exactly the same. So in these cases, we see we can say that the group generated by our set S is the so-called permutation group. And this group is, of course, finite. As for the set of rotation matrices, we have almost the same. This means for the angles 0 and 2 pi, we have, if phi is equal to 0, we have just 3 identity matrices. If phi is equal to pi, we have 3 diagonal matrices, so the set is also not universal. And if phi is equal to pi divided by 2 up to a sign, then our set generates a permutation group. So it is not this is not universal. And the results that I presented today were described now in the paper, which is available in the internet. Thank you for your attention.
Well, I'm still going back to my previous worry. Since the infinitesimal departure from this finite versus infinite order is sufficient to change the status of this element, so in practice that cannot be really controlled because you do not have infinite precision in determining this shape of this gate.
Whether something is rational or is not.
No, but this is a
yes, but if you
difficult to find.
no, I understand all the theorems, but
yes, but if you
level.
No, but if you look at those theorems, you will see that actually what you are saying is not really relevant, because the fact that this product is of infinite order almost always, besides some few really very particular cases. So that's why it's if you change it a little, it will be still of infinite order.
So the important part is that it is of infinite.
Yes.
And these special cases
are very sparse.
Yes.
Yes. There is a finite number of these cases. They are not even of measure 0.
At random, then it is.
Yeah, exactly.
Can I ask a question which is not necessarily related to this particular talk, but to the general we listened to the many beautiful mathematical lectures on the quantum computing. Well, I can speak quite loudly if you want. Well, anyway, we had already several very interesting talks about the mathematical structure of a quantum computing. Is that too much to ask that one of those lectures will be devoted to such a simple product as to show up how do we write a simple algorithm for quantum with these unitary matrices to calculate the sign of x in double precision, for example. I mean, it's fantastic mathematics. I completely agree. But if ever somebody will generate those unitary gates and something like this, there will be someone who will have to sit down and write a program to calculate. I mean, a sine of course, I can retract the sine.
Or cosine.
Yeah, the cosine. Even a to the power x or e to the power x of, well, I will not be so vicious as asking about the program for calculating a logarithm.
That's trivial, because if you don't want to be really fast with quantum computing, you can simulate ordinary computer very easily with a quantum computer, and then you use the Fortran program.
I'm not so sure. These are the statements which I have heard.
I am very much in favor of what Łukasz says. Actually, for the reasons of maintaining and developing civilization in this part of the world, we very much need a set of simple lectures on quantum computing, such that people at the high school level more or less can grasp why it makes sense to study math in order to sometime in the future be able to use or design
I understand.
or program a quantum computer. So I am very much in favor of this idea, and we have specialists here, and I think it's not above their ability to sit down together and produce a set of 2, 3, 4 lectures which we will record and show to the general public. How to compute x plus 2, or how to compute 5 plus 3.
Well, maybe 2 is too much, x plus 1.
X plus 1. And if I may say something, I have to retract my comment because it was wrong. This is, I said that we need all these copies because of parallelization. This is not true. No. Actually, the quantum computer is not equivalent to a set of classical computers working in parallel. It's much more because of entanglement. And this is why we need those copies.
Yeah, but the question is...
Let me acknowledge a comment of that.
Yeah, but the question, how this entanglement is in a practice used to calculate... I mean...
It's not you.
Yeah, but but then it's also interesting answer. If it doesn't help me to calculate the sign of x, then I'm completely I'm much below expressing my incredible fascination with this mathematics which is hidden in talking about the quantum computing. But if it doesn't help me to calculate x plus 1 or x plus 2.
Probably it will never do. Is this but
yeah, well, then it's over. I mean, as I'm concerned.
Something expected.
What?
Factorization of large numbers, that's of course still not
well, but the question is that the Shor algorithm exists so many years, and even in this one device which claims to be the quantum or piecewise quantum computer, which is D-Wave, I mean, it doesn't do this. So the question is whether the Shor algorithm is a mathematical beauty, which is incredibly beautiful and everything like this, but it's pretty useless. Let's say.
Chyba tak.
Yeah, but that is then of course this was the reason why I was saying that the Professor Mankiewicz's suggestion to have a lecture about the X+2 on quantum computing is too ambitious. Let's start adding 0.
First of all, I would like to thank you for your very nice talk. Despite the fact I'm a completely layman person and you lost me a couple of times, I think I get a general picture of your very fine argument. And so it's very interesting experience for me. But as a layman person, I have a layman question. Could you comment quickly what are the practical implications of your finding for the quantum computing information theory?
Practical information?
Well, just the fact that you more or less show us that the order can be infinite or finite. So what are the practical implications of this finding for well, if I would like to process the quantum information theory using qubits and gates?
Do you mean this method?
Yes, yeah. Basically, could you put it for me in the context of the quantum computing and quantum information theory?
Well, to be honest, for me, this work is rather some mathematical proof, some mathematical approach for proving that some important sets of gates generate infinite number of gates or not. However, as it was said, in fact, we know the we don't know any qubit gate with arbitrary precision, but we know only some of its approximation. So, from practical point of view, as Professor Białynicki mentioned, we do not know for sure if our qubit gate has finite order or infinite order.
Actually, it's 10 past 11, so we should probably finish. So let's thank Kasia once again.